very grateful for the invitation, especially as chairman. You know, that makes it all the more desirable to lead the. So I'm going to talk about some questions roughly around the theme of equations defining projective varieties. So this is a circle of ideas that I've been interested in over the years, and it appeals to me for two reasons. First of all, I think the questions themselves have some interest, perhaps. They're kind of in between geometry and algebra. But also, I think this is an excuse to sort of talk about various different methods and different ideas and different questions. So that's the plan. So there are going to really be two topics. The first, which I'll do today, is more what we'll see in a minute, Castelnuovo-Mumford regularity, and then the syzygies will start tomorrow. The lectures themselves are going to be fairly elementary, so it's kind of more a school than a research lecture. So I apologize to all the many experts in the audience. Okay, so I want to sort of start. Let's see. So I want to start with just giving a minute to learn to use this. So I want to start by the questions. You can see the questions that I'm talking about is growing out of two very classical theorems. So I want to start by stating two classical theorems that are basically the motivation. So the first theorem is Serre vanishing. So this is the Serre's theorem. Let's just say Serre. Okay. So recall what Serre vanishing says. You start with a coherent sheaf on some projective space, and then the theorem says that if you twist it up a lot, all the cohomological complexities disappear. So let's consider coherent sheaf on some projective space. And for the moment, I don't really care what the dimension of the projective space is. And then, as you know, what Serre's theorem says is there exists some integer m0, depending on f, so that if you twist it sufficiently, such that if we take some k bigger or equal to m0, and then we twist the sheaf by this power of the hyperplane bundle. So first of all, the f twisted by k becomes globally generated, so the sheaf has a lot of sections. Globally generated. And the higher cohomology vanishes. Okay, so this is one of the first. This is kind of the theorem that put coherent cohomology on the map. And then the question I want to ask is, can we find an effective version of this, effective estimate for this m0? So can one find somehow an effective value of m0? So can we find effectively how much we have to twist by in order that Serre vanishing take effect? And this is the starting point of the theory of Castelnuovo-Mumford regularity. So this really came up when people started to construct Hilbert schemes. So you need to be able to find, in terms of the Hilbert polynomial of m, some effective version, some effective bound for this m0. Now, the most interesting case is to take, and the one we're mainly interested, is to take f to be the ideal sheaf of some subvariety or subscheme in projective space. So let's take x in this PR subvariety or subscheme. The subscheme for the moment is pretty general. And then the interesting case is to apply this question to the ideal sheaf of x. So what is this question really asking? And so we'll call this m0 of x. So we'll say m0 of x is m0 of this ideal sheaf. And so what I want to recall is what geometric information, what classical geometric information is contained in the statement that these higher cohomology groups vanish. So, well, the first thing, what does it mean for the ideal sheaf twisted by k or twisted by m0 to be globally generated? Well, that first condition means that X is cut out as a scheme by hypersurfaces of degree K. So, so X in P is cut out by hypersurfaces of degrees, less than or equal to M naught. So to say, well, let's just say M naught. So to say that the ideal sheaf twisted by M naught is globally generated means that as a scheme, X is cut out by hypersurfaces of that degree. And what about the vanishing of these higher cohomology groups of the ideal sheaf? Well, they mean two things in this case. The vanishing of the H1 means what people called classically that hypersurfaces of degree K cut out a complete linear series on X. So hypersurfaces of degree K bigger or equal to M naught cut out, trace out a complete linear series. So in other words, if we look at the restriction map, maybe I'll put it up here. If we look at the restriction map rho sub K from H naught of OP of K, then so we restrict these things to X, these sections to X. So the vanishing of the H1 means that these maps are surjective for K greater or equal to M naught. So the surjectivity here is the vanishing of the H1 of the ideal sheaf. And then the vanishing of the higher cohomology, H2 or higher of the ideal sheaf, is just the statement that I on X of OX of K vanishes for I at least 1. So that this is isomorphic to H2 of the ideal sheaf twisted part. So to say that you've found an effective value of M naught in the case of these ideal sheaf means, first of all, you know what degree hypersurface you required to cut out X as a scheme, and it means you know that the hypersurface of that degree trace out a complete linear series, and then you know that these higher cohomology groups vanish. So again, this is K being equal to M naught. And so these are the kind of classical questions that arise when you look at Castelnuovo-Mumford regularity for ideal sheaves. And one remark to make is that there are two different flavors of information here. So the vanishing of to say that hypersurfaces of a certain degree cut out X as a scheme, and to say that these they trace out a complete linear series, these two statements have to do with the actual embedding of X in projective space, whereas this is intrinsic to X. So this just involves the line bundle on X. So this is usually easier to control. But so what we'd like to do then, one of the questions is going to be to find out, given some X, to estimate how much you need to twist in order that these classical properties happen. And so this is, as we'll see shortly, the answer to this. This is the theory of Castelnuovo-Mumford regularity. So this is what we'll start talking about from now. The second classical theorem I want to mention, which will be leads to the topic of syzygies, is an old classical theorem of Castelnuovo and others having to do with the equations defining algebraic curves. So the second classical theorem that's supposed to motivate these lectures is Castelnuovo et al. So we start with a smooth projective curve of genus U. And the line bundle on X, on C of, let's say, of degree D, and then we're going to consider the complete, we're going to consider the embedding defined by L. So let's say that the degree is at least 2G minus, let's say 2G plus 1. So then we're in the non-special range. So we're going to consider the embedding of C into projective space determined by all the sections of L. So we want to embed by a complete linear series. And then by Riemann-Roch, that's the dimension. So what Castelnuovo's theorem says is that if the degree is at least 2G plus 1, we're assuming then this curve is projectively normal. So in other words, these maps are surjective automatically for all values of k. So then C embeds as a projectively normal curve, i.e. these maps, piece of k over there, are surjective for all k. And then the second part of the classical theorem says that if we go 1 degree higher, so if D is at least 2G plus 2, then in fact, the ideal of C, let's say C is cut out by quadrics. So in any sense, it's cut out, the homogeneous ideal in fact, is cut out by quadrics. So at a certain degree, when L is sufficiently positive, in this case 2G plus 1, we get projective normality, and if we go a little bit more positive, in fact, C is cut off by quadrics. And so the question, that this leads to is what happens if the degree gets even higher? So what happens if D is 2G plus 3, for example? So in some sense, it's a very natural question, but people, as far as I know, didn't really look at it until the 1980s, when Mark Green realized that these classical theorems about projective normality and generation by quadrics are actually the first cases of a much more general picture about higher syzygies. So the answer will involve syzygies. And another question you could ask is, well, what happens if you replace the curve C by a more interesting variety? So again, there's some slightly less classical work, and actually much deeper, by Mumford and Kemp. Somehow they had studied the analog of Castelnuovo's theorem for abelian varieties. So what happens about embeddings of abelian varieties? So again, this is a very interesting variety. So again, we could ask what happens, what are the analogs of these theorems for more general sorts of events. So that's going to be the second theme of these talks. Okay, so that's the plan. So the first, what I want to talk about today is these questions of Castelnuovo-Mumford regularity, on which there has been some very interesting recent progress that I'm looking forward to hearing about. And there's still in all of these things a number of, I'm going to try to also focus to some extent, at least mention quickly, some interesting open questions. There's a lot that's not known. Okay, so I want to start by, for the rest of the day, I want to talk about Castelnuovo-Mumford regularity and try to understand how you make Serre vanishing. I'm just going to write M-Mumford. This is my abbreviation. Mumford gets a long abbreviation. I was giving a talk once, and I always, this is how I think of Mumford. And I wrote this, and everybody started laughing, and I couldn't figure out why. I realized that they hadn't been reading enough Mumford. Okay, so let me start with the definition. So we start with some projective space P, and I'm probably not going to need to really know too much about the underlying vector space, but I'll call V the underlying vector space. I'm always going to work, by the way, over the complex numbers. So V will be a vector space over C, and let's say a dimension R plus 1. And my convention is the Hartshorne or Grothendieck convention, so this is quotients of V. So what that means is that V is canonically the space of sections of O of 1. And then we'll let S be the symmetric algebra on V. So this is the homogeneous coordinate ring of the ambient projective space. Okay, so what's the definition of Castelnuovo-Mumford regularity? So as Mumford says, it's a strange sounding definition, but we start with some coherent sheaf on P, and we say that the coherent sheaf F on this projective space P is M-regular, where M is some integer, if the following is true. So it's a specific bunch, a specific collection of vanishing. So we ask that the higher cohomology of F twisted by m minus I be 0 for positive I. So if we're on PR, we're asking for R minus 1 vanishings. It's a specific claim of vanishings we want. Okay. And so then the theorem, Mumford's elementary theorem, is that this explains the meaning of Castelnuovo-Mumford regularity. So the theorem is that if F is, let's assume that F is M-regular, okay, so first of all, F twisted by M is globally generated. And moreover, and the maps, and the multiplication maps, so not only is it globally generated, but all the global sections of higher twists of M are determined by the sections of F twisted by M. So let me call this star sub K. The maps from H naught of F twisted by M tensor the homogeneous polynomials of degree K. So you can multiply a section by a homogeneous polynomial of degree K, and you end up with the section of F of F twisted by M plus K, but these maps are surjective for positive K. So in other words, not only is F twisted by M globally generated, but all the higher the sections of all the higher twists of F are determined by the sections of F twisted by M. And then the second feature is that if F, this property, if once F is M regular, it's M plus 1 regular, M plus 2 regular, and so on. And so F is M plus 1 regular. So in other words, to say that F is M regular means that this sort of M, the best M for which it's M regular, is this effective version of Serre vanishing. So this sort of yoga here. So we'll define, let's define the regularity of F to be the least M, so that F is M regular. And then, so this is this regularity of F is the answer to the question, how do you make Serre vanishing effective? So this is kind of more or less the M naught. So the regularity then governs the cohomological complexity. So you see this is an elementary theorem, but what it accomplishes is it replaces having to check, Serre's vanishing, you don't really know where it starts. So here you need to just check R minus 1 vanishings if you're on PR, and then once you hit these vanishings, you know that you've hit the mark from the Serre point of view. And then, as I say, what's going to be particularly interesting to us is what's the regularity of so, well, if we're given a subscheme, and so just as a matter of notation, if we're given a subvariety or subscheme, a projective space, we'll say that the regularity of X is the regularity of the addition. Now, there's an elementary proposition here that says in a stronger sense that if you know the regularity of a sheaf, you really control its algebraic complexity. So let me state a little proposition here. So you see, if you have a sheaf that's M regular, well, this means that F twisted by M is globally generated, which means that F twisted by M is a quotient of a trivial line bundle. Or if you twist by minus M, it means that F is a quotient of a direct sum of O minus M's. And then the kernel that map turns out to be M plus 1 regular, so you can kind of, once you know the regularity of F, you can construct a whole resolution of F, of the kind of module associated, the graded module associated to F where you control the twists. So let me state this principle in a slightly stronger form. So the claim is that if F is M regular, but this is really just a simple application of the Mumford's theorem. if and if it admits a resolution of the following shape, a resolution of the following shape, so actually it took me a long time to go from left to right here. The pros have been doing this for years. I'm always tempted to write, the letters and mirror images. But so we start with F, and then the claim is that we can, I'm going to do this in sheafy sense. It's a direct sum of O minus A0 J's. We write F as a quotient of a direct sum of line bundles, and then we'll get a bunch of O minus A1 J's and so on, different index at J. We keep going. Oops. And the point is that we're going to bound the size of the F. So we keep going. And the important thing is where all the AIJs, we call them APJs, and all the APJs are less than or equal to P plus F. So this is equivalent to regularity. So that says, we can write F as a quotient of a direct sum of line bundles where all the things here are at most O of minus M, then these are at most O of minus M minus 1, and so on. And this actually, as long as F doesn't have any zero-dimensional embedded pieces, this actually stops after our steps. So basically, we're controlling the degrees of the generators of all the syzygies of F. So in other words, the regularity of F controls, bounds, let's say, the degrees of the generators of all syzygy modules. Syzygy sheaves, let's say. So in this very strong sense, knowing the regularity of a sheaf bounds its algebraic complexity. And in fact, if you give the program Macaulay a sheaf and you ask it to compute whatever you want with it, the running time in principle, the sort of what bounds the sort of how long it takes is the regularity. I've already started confounding algebra and geometry here. So there's an algebraic analog of this notion of regularity, and I'm not gonna I'm gonna kind of confound them a little bit. There have to be. So if you start with if M is a graded S module, remember S is the homogeneous coordinate ring. Then in particular, or an ideal I in S, there's an analogous notion. One can define the regularity of M. And so you can define it by a local cohomology, by analogy to what we did with sheaves, or you can define it by the regularity of a module is bound, kind of controls the highest degree of a generator of a syzygy module when you take the resolution. And if I is a saturated ideal, then this is essentially the same thing. Then the regularity of this homogeneous ideal is equal to the regularity of the corresponding sheaf. So the two theories are if you start with a module that determines a sheaf, and for most practical purposes, the regularity of the module or the regularity of the corresponding sheaf are equivalent informations. Okay, so that's the definition and the basic properties, and so where does some geometry come into the picture? Well, so the real geometric question is, if we start with a sub-scheme or a sub-variety of projective space, so the basic question is that given a sub-variety or sub-scheme X inside some projective space, how can we bound the regularity of the ideal sheaf? So what we want to do is one wants to bound the regularity of X in terms of geometric or accessible algebraic or accessible algebraic data. So if I give you a subvariety or subscheme of projective space, how long is it going to take Macaulay to compute the resolution of X? And so this is really the kind of interesting question. And there was a very influential paper, I think it came out around 1990, but it had been floating around, or maybe that's when the preprint came out, but it had been floating around, the ideas had been floating around before that. There's this very interesting and still mysterious dichotomy that I think is still not really completely understood, but there's been, I'll say in a second, a lot of progress. So this was really, the point of view was emphasized in this paper of Varieties-Mumford. So it turns out that there's, if you take a smooth variety X, so for a smooth subvariety of projective space, let's say X, and again, I'm not, in projective space, complex projective space, the regularity is bounded linearly in terms of geometric data. Reg X is bounded, I'll state the precise theorems later, but linearly in terms of geometric data, algebraic data. So the regularity grows linearly. On the other hand, for arbitrary schemes X, the regularity can be huge. So for arbitrary schemes X, regularity can grow exponentially. So there are examples, which I'll mention later on, actually doubly exponentially. Exponentially. So there's a wild difference between arbitrary X and smooth X. And for a long time, I think one of the main open questions in the area is if you take a reduced and irreducible X, which side of this chasm does it lie on? And there's been some very interesting work that I'm looking forward to learning about by Jason McCullough and Irina Piva. And essentially what they've shown is that they have a very nice construction that basically for reduced and irreducible X, they can be crazy. So this was, I think, answering one of the big, so reduced and irreducible X, I should have on the dark side, can be on the dark side, so it can be complicated, can also be that. Okay, so I'm looking forward to learning about this. But it's still, to me, somewhat mysterious about why this is happening. And another question I'm going to raise later on is that the examples of kind of arbitrary schemes that are crazy are really very combinatorial in nature. And I think they're still not really understood geometrically. Essentially what McCullough and Piva did is that they have a very nice construction starting with a bad X. It's a kind of a blow-up construction. You blow up a funny ideal and you get a reducible variety that inherits the regularity of X. But somehow it's still not clear, at least to me, what's going on with these crazy X. So let me do a couple of examples, and then I'll state the theorems that I'll prove in the next lecture. So let's do some examples here. Okay, so let's start with the projective variety and take a very positive line bundle on it and ask what we can say about the regularity. So X will be some projective variety of dimension n. And we'll take L to be some line bundle on X, which defines an embedding of X. And again, it's critical that I want to look at the complete linear series of X. So it will be very ample, and we'll define an embedding of X into some. I use all the sections of L define an embedding into some projective space. And I want to assume that L is sufficiently positive so that we're in this kind of Serre vanishing range. So first of all, this X in projective space is projectively normal. And that the higher cohomology of L vanishes. And it's quite easy to arrange for this, for example, in terms of collider vanishing. If you take L to be the canonical bundle plus something, it's easy to do this. Okay, so we embed X. So for example, this is like we're in the range on curves where the degree is at least 2g plus 1. Okay, so we get this n-dimensional variety X, and we can ask, well, can we say something about its regularity? In fact, it's very easy now to compute the regularity. So this is basically an exercise. So then the regularity of X is at most n plus 2, if I've got my numbers right. And the regularity of X, well, it's either n plus, let me say it like this. The regularity of X is either n plus 1 or n plus 2. And the regularity of X is equal to n plus 1 if and only if all the cohomology hi of X, actually we just need the hn to vanish. So hn of X, Ox vanishes. So in other words, it doesn't have any pg of X. And this is the same thing as there are no canonical forms. Okay, so this is a little exercise. But the moral of this is that if you take an embedding defined by a complete linear series on anything, then essentially you can completely compute its regularity. And there's no ambiguity. And on the other hand, if you were to take an incomplete linear series, for example, if you were to study the regularity of Pn, then I think knowing the regularity of different embeddings of Pn is probably, in practice, if you can control that, you can probably answer any of these regularity questions that are going around. So if you have a sort of a variety that you know a little bit about, you take a sufficiently positive embedding of any variety, and you look at the complete linear series, then you can completely control what happens. Okay, so for many of these regularity questions, the whole problem is that if you're given a variety in projective space, it may or may not be projectively normal to begin with. Let me do another example. When I've lectured on this stuff in the past, I've done the example. So as an exercise, if you've never done this, you should look at exercise. This is explicitly an exercise. Compute the regularity of 4 points in P2. Regularity in syzygies of 4 points in P2. So I'm not going to do this. So there are 4 points. If you take 4 points in the plane, they come in 3 different flavors. You can have 4 general points, which are complete intersection of 2 conics. You can have 3 on the line and 1 not on the line. You can have 4 on the line. So it's fun to do those. So I want to do another example that I'm not sure. This is one I like. I'm not exactly sure what it's an example of, but it's a fun example to do. So let's do this. Okay. So let's take, again, it will be curves in the plane. So this may be kind of a counterexample to my philosophy, but we'll see. But anyway, it's a fun example. So let's consider 2 curves in the plane. 2 curves in the plane. Consider 2 curves. And I'll do this classical thing. I'll confound the name of the curve with the names of the defining equation. So F1, F2, and P2 of degree D. And let's assume that they meet transversely, so then they'll meet in d squared points. So we have 2 curves in the plane meeting in d squared points. And here are 2 cubics meeting in 9 points. So the number of points in Z is d squared. So of course we can certainly compute the regularity of Z, so let's do that. So I mean, if you have a complete intersection, you can, its ideal is resolved as by the Cazul complex. So we have the Cazul resolution I of z. It's generated by two curves of degree d, so OP, two copies of minus d, and then there's the one Cazul relation between them. Okay, so this is the resolution, of course, of a complete intersection. And then we can use that proposition I stated earlier. So how you compute the regularity from this is you start with minus 2d, and then if you were to add 1 to this, you would get 1 minus 2d, and then 2d minus 1 is the regularity. So by this proposition we stated before, the regularity of z is 2d minus 1. Okay, so this is not the example. That's brief. But now, let's do something fun. Let's take one of the points of z, so I'll call it this one p, and remove it and see what happens. Okay, so let's take one point in z, and then we'll take x to be the remaining points. Okay, so let's take a point p in z, and then let's take x to be the remaining points. So x is now a collection of d squared minus 1 points. And let's try to ask what's the regularity of x and what does the resolution look like. Now, one of the things that happens when you play with regularity is to make statements that can go on. I mean, it's very hard to find examples of regularity. So you might say that if you have a given scheme and you have a subscheme, the regularity of the subscheme only gets better. And there are a lot of statements of that type that kind of sound plausible that then become famous conjectures for 20 years, not because there's much evidence for them, but nobody can find examples. But on the other hand, it is true for finite schemes that if you have a subscheme, the regularity gets better, just if you run So, and in fact, we can see it's sort of an exercise, where we'll see this in a moment, an exercise that in fact, the regularity of x improves. So the regularity of x, this is basically it's 2d minus 2. It gets smaller. So we'll see this in a minute. This is essentially the Cayley-Backrack thing. It says if you take all but one of the points of z, any curve of degree 2d minus 3 lying on all but one of the points of z lies on the remaining one. So passes through the remaining. But anyway, so the regularity has improved. But let's see what happens to the syzygy. So this is kind of fun. So this p is of course it's a point. So let's write p as L1 equal L2 equals 0. So p is the intersection of two linear forms, two lines. Okay, and now because we can write f1, because p lies on the intersection of the f's have to be linear combinations of the L. So we can write f is a11 L1 plus a12 L2, and f2 is a21 L1 plus a22 L2, where the degrees of the a's are what would then be d minus 1. Okay. Good. Now, so the star in this little game is let's take delta to be the determinant of this A matrix. It's the determinant of A11, A12, A21, B22. So this now is a curve of degree 2d minus 2. And it's an exercise that, in fact, basically just look at when you can solve these equations. The delta is now a minimal generator, of the ideal of x. So if you remove, when you take this x, which is once you've removed all these other points, this delta, which has degree 2d minus 2, passes through all the other points. So just ask yourself, when can you solve these equations? And so now you can, here's what the resolution of X looks like. So let's see if you can write this down. I'll write it down and I'll leave it to you to check that this is okay. Okay, so the resolution of the resolution of the ideal sheaf of X looks like this. So we've still got these two curves of degree minus d passing through X, but then we've also got this new thing of degree 2d minus 2. So we get a minimal generator like this, and then now there are true relations among these of 1 minus 2d squared. And you can see what the matrix is. This is the matrix. From here to here is the matrix of A, but here is the L's. So see what's happened here is that the regularity has gone down because we have 1 minus 2d, 2 minus 2d. So the regularity has gotten better, but somehow the resolution has gotten more interesting. So this is the kind of thing that can happen. And so the regularity is kind of easy to control, but then exactly how that plays out in the resolution can be tricky. So here the regularity is not witnessed by the degrees of generators, but it is witnessed by the degrees of the syzygies, but here it's actually witnessed by the degrees of the generators. So funny things can happen. So it's fun, you can go home and play with some examples in the plane. Okay, so let me now talk about regularity bounds and state some of the results. So again, the question is, what given an X, what can we, so we want to bound the regularity of some subvariety or subscheme X in projective space. And there are various invariants you could use. The one that not everybody agrees with it, the one I kind of like the best, to me is somehow natural, is to start in terms of the degrees of defining equations. So let's say in terms of some kind of data. So what I want to, for now, I want to use use the degrees of defining equations. So one of the more famous questions is to use the degree of X, but I'll talk about that next time. Okay, so we imagine that X is cut out as a scheme by equation, so polynomials of degree D. So what can we say about the regularity? Well, of course, we should start the simplest thing that's cut out by equations of a given degree is a complete intersection. So here's let's say, suppose we have xn, now I need to be a little bit, PR is a complete intersection of hypersurfaces of degree, let's make them all the same degree, of degree D. Then you could compute, as before, as we did for curves in the plane, you can completely compute the, and then let me let E be the codimension. E is n, r minus n, so it's the codimension. This is the number of defining equations. And then you can compute the regularity, and let's see what you get. It's E times the degree of the defining equation minus 1 plus 1. So again, notice that this is linear in D. It's linear in the degree if I have reason to call, I sometimes call that complete intersection regularity. So that's a kind of a baseline example. And so a little theorem that we noticed some years ago with Lawrence and Aaron Bertram is that in fact, if you take a smooth thing, so with Bertram and on, so I'll prove this in the next hour with multiplying girls, is, okay, so let's consider a smooth xn in PR, and again, E will be the codimension. I'm always working over C. A smooth subvariety cut out scheme theoretically. Let me write out smooth in words because that's important. Smooth subvariety cut out by as a scheme, so scheme theoretically by hypersurface of degree D. So in other words, the ideal sheaf twisted by D is supposed to be assumed to be globally generated. And then the claim is that you get exactly the same, it's bound, the regularity of X is bounded by complete intersection regularity. So then you're no worse than that. So is it most, what is it, E times D minus 1 plus 1? So again, it's linear in D. And in fact, equality holds if and only if X is a complete intersection. Okay. So if you're willing to accept as kind of input data the scheme theoretic degrees of scheme theoretic defining equations, then you get a best possible bound on the regularity, and in fact it emerges that complete intersections somehow have the worst regularity, just as we saw in that example. So particularly the regularity is linear in the defining degrees. On the other hand, there's this famous example by Meyer and Mayer and Bayer and Stillman. Meyer and Mayer, Bayer and Stillman. That if you look at arbitrary schemes, the picture is completely different. So there exist non-reduced subschemes, X in PR, cut out by hypersurfaces of degree D, such that the regularity is, well, you have to be careful with, it's D to a very high power, and it's doubly exponential in the number of variables. So the regularity of X, is bigger, it's approximately D to the 2 to the R over 10. So it's not only nonlinear in X, it's nonlinear in D, it's a power D where the power is exponential in the number of variables. And in some sense, this is the best possible. So there's another result of Giusti and Gallego. That gives a bound, an upper bound having the same shape. So if Ix of D is globally generated, then the regularity of X is at most something of the same shape, 2D to the 2D. So it's not quite the same, but it's the same rough shape. So somehow what can happen for smooth things, as we'll see in the next hour, the picture is completely tame, and for arbitrary schemes, the situation is completely wild. What's not clear to me, and I asked this as actually a question for maybe Jason or others in the audience, it's not totally clear to me what happens for reduced and irreducible. So what about reduced and irreducible? So I'm not claiming this is an open question. I actually don't know the answer. It wasn't clear to me whether the construction of McCullough-Peever answers this question like this, because there's something that comes into the construction that's a little bit. Anyway, so maybe somebody can tell me the answer to this. So this is kind of the basic setup. So, and I think in some sense it's still mysterious, at least to me, what's really going on here. So for smooth things, at least in terms of these defining equations, everything's fine. There are these funny examples of wild regularity, and who knows exactly what's going on. So in the next hour, I will prove this theorem. So this uses some vanishing theorems, and you can certainly do it without multiplier ideals, but this gives me an excuse to talk a little bit about multiplier ideals. So I'll show you the proof of this with multiplier ideals, and then I'll talk about some of the other questions that people have looked at. Okay, so that's the first one.
We'll have time for one or two questions if someone has them.
Yeah.
So you mentioned that the regularity of subscheme can be improved can be like greater than, can be better than the regularity scheme. Is there any known like higher dimensional example?
Yeah, I mean, so, I mean, of course, if you have a nice, I mean, obviously, if you take a so I don't know many, yeah, so you can try to, I mean, so for example, it's not, you could take a scheme that has, like there was this conjecture that was never, who was this guy? MS Ravi. So if you have a, if you take a subscheme, is the regularity of the reduction better than the regularity of the subscheme? So there was no reason to imagine that that was true, but there's really only one, there's one person, Marc Chardin, who's the world's expert at finding examples. So he finally, after 20 years, found an example for that. So there are all these, you know, people have asked, like if you have an ideal and you take its integral closure, is the regularity. So I always bet against, I mean, if you give me a statement like that, I would always bet against it. But you could take, you know, ages before somebody can find a counterexample. Because the whole problem is that there are not many methods of construction. But for points, it's sort of silly, because if you have, you know, if you have x and z and this is finite sets, then, you know, you have the ideal of, which way is this going? You have the ideal of z sitting inside the ideal of x, and you have something on 0 dimensional. So of course, the h1 can only decrease. So, yeah, so.
Any other questions? Let's thank Rob again. We'll have a small tea break.